Hi everybody, this is Dr. Smith. Welcome to Chemistry 2510, experiment number 5. This week in the lab we're going to do the esterification of benzoic acid using a Fischer esterification. And then you'll also do the recrystallization of the acetanilide that you separated out in the previous experiment. So in lab 3 you separated benzoic acid and acetanilide, and the acetanilide's been sitting in your locker. We're going to have a chance to go back and recrystallize that this week. Okay, so before arriving at the lab, what are the things that need to be done? I think you're getting used to this sort of slide now. So make sure you read the procedure for experiment 5. I've shown you the page numbers here in the lab manual. Watch this video, so hopefully you've read the experiment already. Prepare your blue lab notebook as required. Now this week, for the first time, we're going to do an actual transformation. You're going to convert a carboxylic acid, your benzoic acid, into an ester. So we're doing a chemical transformation. Therefore, this procedure needs to be a preparative format. So go back to section 1 in the general protocols and look at the difference. One major difference is you need to have the reaction written out, that transformation reaction written out. So that needs to be there. Also in your table of physical constants, it requires you to put in the number of moles and grams of the reactants, so you can immediately know, if there's a limiting reagent calculation you need to do, you can figure out the limiting reagent, and you can do yield calculations based on the number of moles, which is illustrated right in your table of physical constants. Okay, so go back and look at that preparative format and follow the preparative format requirements for the write-up. Okay. Just so that you know, there's no lab report for experiment 5, so you won't have to hand in a lab report for experiment 5. However, data that you'll collect in experiment 5 is required for you to complete lab report 4. So it has to do with the acetanilide. So the recrystallization, you'll get melting points and masses and so on of your recovered and recrystallized acetanilide. That's going to be required to complete lab report 4. So once we've gone through next week and we've gotten that data, then we'll announce at some point in the future when lab report 4 is actually due. But it's not going to be for at least another week. Okay, so what are the outstanding tasks for experiment 4 that need to be also done this week before or during the experiment 5? Remember, you need to take masses and melting points of your purified benzoic acid. Do that. The reason why that's so critical is you're going to use your benzoic acid, so you need to, before you go and use it, you need to determine the mass so you can use that number in future calculations. You also need to either take a melting point or set a small sample of purified benzoic acid aside to be able to do those melting points. So you can take a small vial, blacktop vial, and put a small amount, enough for maybe 3 melting points in it. You're also going to have to reserve a small amount, say 5 milligrams, for recording an IR. An IR really needs about a single crystal, so it doesn't require a lot, but remember to set some aside for both of those procedures. And also you'll have to sign up to run a purified benzoic acid sample on the FTIR, and that will be something that we're currently looking at running outside of lab time. So for that last part, we may change that once you come into the lab this week. We're just going to see at the beginning of the week if we can still carry this out. We'll make a decision and let you know when you come into the lab. So if you come into the lab, maybe we're going to tell you don't have to run the IR, but I would really like to have you come in and run the IR if at all possible. So we'll see in the future. We'll see this week how things work. For experiment 5, you're going to do the esterification of the benzoic acid. Then you're going to do solvent-solvent extraction, working up the reaction mixture and so on to isolate your methyl benzoate ester product. And kind of as a separate operation, you're going to do the recrystallization of the acetanilide. Okay. So what's involved with the esterification and the isolation of the methyl benzoate? You're going to do the reaction under reflux. So this is a new technique. We'll talk about what's involved in a reflux. And once that reflux is complete, you're going to do the separation and the purification of that methyl benzoate product. And just to prepare you, you're going to have to do 6 sets of extractions, a couple with water, and then you're going to do some other extractions, and then more with water. We'll talk about those in more detail in a little bit. And then this recrystallization of the acetanilide, and the solvent that you're going to use this week is water. So you're now experienced with using water for crystallization, but there's a bit of a twist in this one this week. Acetanilide, because of its melting point, as you're heating it up, it will most likely oil out. So rather than like the benzoic acid where you had solid in it, you had to keep adding water until the solid finally dissolved at the boiling point. With this one, the acetanilide may actually melt as you're heating the water up, because the acetanilide is quite crude, and the water actually acts as an impurity here. So quite often, as you're heating it up, it melts and you get an oily material that's acetanilide, but it's in liquid form rather than in the solid form. So it adds a little bit of a hurdle working around that. Some solids, when you try to recrystallize them, they behave this way, so we've got to become used to it. When we look at the cradle to grave map of the experiments, here's where we are. So we're going to do the purification, take the purified benzoic acid, convert it into the methyl benzoate, and at the same time you're going to do the recrystallization of the acetanilide to give you the purified acetanilide. So once you set up your methylation procedure, your esterification procedure, that has to reflux. It has to boil under reflux for about 1 hour. And that will give you time to then do the recrystallization of the crude acetanilide. So you're going to have to juggle both those things this week in lab. So let's go through this whole idea of converting the benzoic acid into the methyl benzoate. This uses a reaction which we've just recently seen in lecture, the Fischer esterification after Emil Fischer. So let's take a look at what happens. So here's kind of, we put the flow chart of purification in here just to sort of give you an oversight on how that's going to work. So we're going to do this reflux. We'll set it up and we'll do this reflux. Let me convert back into a pen. We'll do this reflux. And at the end of it, you're going to take that reaction mixture and you're going to transfer it to a separatory funnel. And you're going to do some extractions. You're going to add water and do an extraction. And then you're going to perform some other extractions. You'll extract again with water. And I think actually what we've done is we've changed this in the procedure. You'll see in a slide here in the future, in a couple of minutes. I think we've decided to do 3 extractions with water and then extractions with bicarbonate. So you'll see this. There may have to be an adjustment to this flow chart. So pay attention as we move through the slides. So you see again how we're doing the separations, and we're following, okay, where do we get rid of these impurities? How do they disappear from the setup? So you can work yourself through that. I've shown you the sections that are discarded. From this, you'll isolate a crude methyl benzoate. And then at the beginning of experiment 6, you're going to use the methyl benzoate. So we'll start by doing a distillation to purify the methyl benzoate before you use it in the next step in the procedure. So here's the transformation you're going to achieve. You're going to convert a carboxylic acid into an ester. And the thing to think about is how can we accomplish this transformation? So what are we going to want to add as a reagent to make this happen? So now we know that what we would like to add is the alcohol. If we want to make the methyl ester, we would add methanol. And if we add those together, like is shown on the slide, what's going to happen here? And the answer to this is just sort of say, you add these together and they will sit there and smile at each other and wave, and nothing will change. So we need to catalyze this process. And now you know that you need acid. So H2SO4 is the acid of choice. And we're going to apply heat. Now, in theory, any acid would do in this case. But one thing to think about, what if you added HCl? What would happen? What if you added nitric acid? What would happen? Well, if you added nitric acid, HNO3, that's the reagent for doing a nitration reaction. So you might actually do a substitution on the ring of benzoic acid, and you wouldn't want to do that. Adding HCl, well, HCl, you can add it as a liquid, but that's an aqueous solution of HCl gas. HCl in its sort of normal form, as a pure form, is a gas. So when you have a concentrated solution of HCl, it's dissolved in water. And if you look at this reaction, what are the products in this reaction? Your ester, but also water is a product. If you were to add a reagent that's dissolved in water to this reaction, what would happen? Well, Le Chatelier says it would push it back towards starting materials. When you add water to this reaction under these conditions, you push the entire reaction back towards starting materials. So that you wouldn't want to add HCl solution to this reaction because it's actually going to be harmful in you achieving high yields. Okay? So the acid catalyst is required, and also you don't want to add any water to this because it will be detrimental to your yields. So knowing that we need an acid catalyst, how do we think that this reaction works? What's the mechanism? So if we look at some of the empirical evidence from the people that studied this reaction, there was a couple things that they knew. Since the acid catalyst was required to have this reaction proceed, they knew that the acid was required in the rate determining step in the process. And also, when they did labeling studies with oxygen 18, and they used methanol as the source of oxygen 18, that oxygen 18 was incorporated into the ester, and it was incorporated at the alkoxy oxygen, not at the carbonyl oxygen. Okay? So whatever mechanism you have to develop for this, that alcohol oxygen should end up in that position, right? So it kind of helps us, it helps guide how we develop the mechanism. And that's kind of the fundamental way under which these mechanisms were developed many, many moons ago, okay? So now if we think about starting with benzoic acid, treating it with an acid catalyst, where do we expect the protonation to happen? So remember, we've had this discussion already in lecture. We have two possibilities. We could protonate the carbonyl, or we could protonate the oxygen of the OH group. So I've shown you here what the outcome is from protonating each of these oxygens. And Dr. P is now, he's trained into you. When you protonate a carbonyl, or when you protonate a carbonyl containing compound, you protonate the oxygen of the carbonyl. So you now know it. But we've been talking more recently about why. So if you look at these two possibilities, that bottom molecule, there's no resonance form to stabilize that overall reactive intermediate. That cannot be stabilized by resonance. And if you consider putting a positive charge on the oxygen adjacent to the carbonyl, remember that carbonyl already has a big delta plus on it. Okay? Having that oxygen pulling more electron density away, it's kind of like it's already in pain, and that oxygen just making it worse. It's really, it doesn't like that at all. Where up on the top example, now you can get out your red pen and start to push some arrows around, and sure enough, there's resonance stabilization that happens, so we can spread that charge around. And there's another resonance contributor that I haven't shown here. I haven't shown the other obvious one. This one that I have shown here, it's not a very significant contributor, but think about if you can figure out what the other one is. And here's kind of a hint. It may look like the first contributor, but it's not, because the oxygens are different, right? So think about that. There should be another resonance contributor that you should be able to come up with. You may want to go back and look at your lecture notes to see what that other resonance contributor would be. And even think about the hybrid. Draw the hybrid from your resonance contributors and figure out exactly where the charges are and so on. So now let's keep going on this reaction, and I'm not really going to draw it as a complete mechanism. Like, for example, you need the other resonance contributor there to get full marks if you were doing a mechanism. Here I bring in the methanol, and I'm having the methanol attack that resonance contributor that has a full positive charge on the carbon of the carbonyl. Again, like we've talked about in class, you could attack any one of the resonance structures and complete the mechanism. So now we've got this new reactive intermediate on the bottom. So how do we proceed? Well, it's a good question. A bunch of things happen, and eventually out pops a water molecule as a product and the ester. So I want you to sit down with pencil and paper and develop that reaction mechanism, and we've asked for you to include that reaction mechanism in your notebook. Okay, so think about how this is going to work, and then go through the steps of writing out that full mechanism. Okay. Now, here's something. In looking at that reaction, we go from a carboxylic acid to an ester in the presence of acid. And if you look at the other product, it's not only an ester, but it's an ester plus water. So an ester plus water in the presence of an acid. Hold on, we've seen that reaction as the hydrolysis of an ester to give the carboxylic acid. We've seen this complete reaction mechanism in reverse. This is a reversible process. So how do you influence where this reaction goes? Does the equilibrium lie on the starting material side? Does it lie on the product side? And the answer to that is, it depends on what you want. So you can influence the position of the equilibrium by doing various things. Okay, so all steps are reversible. It has an equilibrium constant of about 3. So it does lie a little bit in favor of the product. Okay, but an equilibrium of 3, it still means the yield is very low. So at very best, with this equilibrium constant, if we added 1 equivalent of acid to 1 equivalent of alcohol, we would get approximately 35% yield at best. Okay, so what are we going to do? How are we going to increase the yield? Well, what Le Chatelier said, if you want to push a reaction from the left to the right, what you do is you do something to apply pressure to the left-hand side. What he meant by pressure was not necessarily, the number of atmospheres, but what he was talking about is if you increase the concentration of your reactants, that applies a pressure, and that pushes the reaction towards products. So here what we're going to do is we're going to increase the concentration of our reactants by increasing the concentration of methanol. We do the reaction in a solvent, which is methanol, and that pushes the whole reaction towards completion, okay, via Le Chatelier's principle. Okay, how do we do this? So we want to heat up the reaction mixture. The reaction mixture contains your benzoic acid and methanol. But methanol has a pretty low boiling point. So if we're heating this up, wouldn't the methanol evaporate? And the answer is, yep, it would. If we don't do something to prevent it, it's going to evaporate. So what do? We use a reflux condenser. So a reflux condenser is our condensing tube that we've used already. We used it in the steam distillation. But now what we do is we attach it directly to the round bottom flask, which is where the reaction is taking place. So in this picture, you will see the heating mantle. The heating mantle's here. And down inside, it's a little bit difficult to see, but down inside is the round bottom flask. In that round bottom flask is the reaction mixture. It has the benzoic acid, it has methanol as the solvent, and it has the acid catalyst, okay, sulfuric acid, and we've added some boiling stones. And we've attached directly to the round bottom flask a reflux condenser. You flow water in through the bottom. Okay, so here I've shown with arrows, the water goes in through the bottom and the water comes out through the top. If you hook the tap up to the top tube, the water will run into the condenser, run the side, down the side, and run right out the bottom tube, and water will not fill the condenser. Okay? So this is the way to hook this up. It sits up on top of a lab jack. There's only one clamp that's used in this apparatus. That one clamp is firmly secured at the mouth of the round bottom flask. Okay, so where this red arrow is pointing. Make sure that that clamp is well tightened on your flask, and make sure it's connected very tightly by the clamps that hold it on to the lab frame. Okay, it should stand up firmly without sitting in the heating mantle, because later on you're going to have to drop the heating mantle down, and if this is not clamped well, it will actually fall down. And it could break the glassware and destroy your reaction mixture, and you'll have to start again. So please make sure, be very mindful of the clamping. And as we're coming up on lab practicals, I would emphasize this repeatedly. Quite often when things happen in lab practical, it's due to people not focusing on making sure their clamp is secure. Okay, so if you have questions about clamping, please talk to us. But clamping is a really critical issue. Okay, one clamp right at the mouth of the round bottom flask, nice and tight, secure. Okay, make sure you don't forget boiling stones, because this is a boiling reflux, so you're going to need boiling stones in there. So what will happen is the methanol will boil, and it will come up the round bottom flask and into the condenser, and as soon as it hits the wall of the tube has been cooled by the cooling water. Once those hot vapors collide with that cool wall, then they recondense. They lose all of their energy, and the molecules start to stick back together again through intermolecular forces, and then they run back down into the flask. So it's kind of like, it's not a closed system, but it's a circulating system where that evaporating solvent condenses and drips back and down into the reaction. It keeps a constant volume in the reaction mixture. Once you've completed the reaction and you've allowed it to cool down so that you can handle it, I want you to transfer it into your separatory funnel, add some dichloromethane, and then add some water. Okay, and you're going to do that extraction and the separation. Once you get the organic layer, your methyl benzoate will be in the organic layer. You're going to wash that organic layer with an additional 2 portions of water, 2 15 ml portions. Then you're going to proceed to washing it with bicarbonate. Bicarbonate solution, as bicarbonate is shown here, is a base. So it will mop up any excess acid. Okay? It will also deprotonate any unreacted benzoic acid. Okay? You're going to do 2 washes with sodium bicarbonate. Be very careful with the sodium bicarbonate. So you've been doing active extractions. You did one last week. You'll do another this is now another active extraction, but it's a little bit different. When this base removes acid, it converts it into carbonic acid. Carbonic acid falls apart to release carbon dioxide. So you're going to produce carbon dioxide, i.e. a gas, in your separatory funnel. So you need to be venting that gas off so it doesn't build up and something bad happens, okay? After you've done the bicarbonate extractions, you're going to do one final extraction with water to remove any remaining bicarbonate, and then you're going to separate off the organic phase, dry it with magnesium sulfate, and continue along. Put it on the rotovap. Okay, so here's where I'm saying with this reaction with bicarbonate, when bicarbonate reacts with acid, you get carbonic acid. Carbonic acid is in equilibrium with its gas state carbon dioxide and a molecule of water. So pressure, this means pressure. So be careful. You're going to have to vent often. Don't leave your top on your separatory funnel when it's sitting on the ring clamp in the fume hood. Really important for this week's lab. Okay. Okay, so we're not going to go through the details of these, and you're going to dry with magnesium sulfate. One last opportunity to make sure you understand how much magnesium sulfate to add to dry a solution. This continues to be important. Then you'll filter off the spent magnesium sulfate. You'll rotovap off the dichloromethane, and then you're ready to go. So that oil that remains in the round bottom flask, you'll leave in your locker until the following week, and we'll come back in lab 6 and do a distillation on that crude methyl benzoate, and then we'll continue on. We're going to do a nitration experiment where we'll nitrate the ring of the methyl benzoate. Just back to recrystallization. So remember the recrystallization of the acetanilide. You have to go through the same procedure once again. We're telling you it's water, so you're not going to have to figure out what the solvent is. We're telling you right up front it's water. Normally, you would have to do a solvent selection by testing small amounts and various solvents, room temperature, heat it up to the boiling point, cool it down, just like we did last week. This one, we're just going to tell you, use the water as the solvent. So you need to dissolve your crude acetanilide in a minimum volume of solvent, water, hot. Okay. Now, some of you were adding a whole bunch of solvent and then starting to heat it up. And in some cases, I'm worried that you might add too much solvent to begin with. By the time it dissolves, you're not saturated, so your yield is really low. Please don't put your sample, your dry sample, on the heat until you've added solvent. So just add enough solvent to cover the bottom of the Erlenmeyer flask, then start to heat, and then as necessary, add more water to it so that you don't run into a situation where you've added too much. Once you've got it into the minimum amount of solvent, you want to filter off the impurities. Now remember, we add an excess of solvent to give you a little bit of time for it to cool down. But the filtering while hot removes any insoluble impurities. Watch for oiling out. If it's oiling out, you'll add more hot solvent. Now, oiling out, most of you will have oiling out this semester, or this week in lab. And the reason is the oiling out happens when your solid melts before it dissolves. Okay, so as you're trying to add more solvent, it can actually melt because of the temperature. It hits its melting point. So here, in this case, the solvent is behaving like an impurity, and therefore the melting point really drops down for acetanilide. So you still continue. Once it melts and you have oily droplets, you need to keep adding water at the boiling point to get those all into solution. Okay, so here's an example of a recrystallization. And I want to point out to you over here on the side, there's a blob of oil. So some of the compound has gone into solution, but you get this oily mass that can collect on the flask. You need to continue to add more water. This is just a zoom in on that same photograph. So again, you can see these brownish globules of oil. Okay. So you just need to add more solvent and continue to heat it back up to the boiling point, and eventually that oil will dissolve. Now, what it may leave behind are small particles, with color associated with them. So maybe black or dark brown particles. That's where the color was coming from in your crude sample. You're not trying to dissolve those black brownish particles. You're trying to get rid of the oily stuff. So look at the flask and see the oily stuff. That's your acetanilide that you need to get into solution. So once you've got it dissolved and at the boiling point, add an additional 10% of the volume of your solvent to that point. Bring it back to the boiling point. So this is meant to just give you more time to do your hot filtration without crystals starting to form. Once you've done that, do the hot filtration. Allow it to cool slowly over on your bench, sitting on a pack of papers, just so that it cools slowly. And this acetanilide forms plates. So it forms horizontal plates rather than needle-like crystals. So it looks a little bit different. I think it's kind of cool. Then vacuum filter the cold mixture to get your acetanilide, your purified acetanilide, and then wash the crystals with cold solvent. So in this case, water. Okay. So here's the result of slow cooling. You'll see some crystals in the bottom of it. Okay. Once you've done the vacuum filtration, this is what your crystals will look like in your Buchner funnel. Okay. So they're shiny plates rather than the sort of fine needles that you had last time. That's the end of my presentation. So hopefully, things are pretty clear from that. So good luck in the lab this week. Keep looking for ways to make your actions there, more efficient and more well planned. Just keep improving. You're doing a good job, but we can always be better. Lab practicals are a few weeks away. So keep that in mind, not to panic or freak out, but just to look for ways to become better at doing the same kinds of things that you do. This week you've got more tasks to juggle perhaps, so time management becomes an issue, making sure you sort of order when you're going to do things and so on. So you're getting good at that, so keep it up. Okay, thanks everybody. Bye-bye.